So I'll try to walk slowly. I think there's a very loud, right? Through the topic, and of course, stop me anytime you have any question. So indeed, I will be talking about evaluating graph embeddings, and this is kind of joint work with François Teberge from TAT and Bogumił Kamiński, and also I think Łukasz Krajiński was involved at some point as well. And so we'll see all of that here. So let me just jump straight to the topic, and I'm reheating, of course, my presentation. My goal is always to keep the same slides for at least 2 talks, so that it's justified to spend substantial amount of time to produce them. So I'm reheating a presentation that I actually gave for students from Netherlands the other day. That were visiting TMU, and here, I spent a bit of time motivating why we care about networks, but I guess for this crowd is kind of silly. So I'm going to go very quickly through the first part, but then jump to graph embeddings, and the main attraction is our framework to benchmark graph embeddings in an unsupervised way, and hopefully I will be able to hit a little bit of algorithmic issues, because there are many things I could talk about, but I guess maybe algorithmic aspects are of interest to this crowd. So I guess my motivation is, again, I will be going very quickly through that part, but I'm motivated. I don't know if it's a good motivation, you will be the judge, but I'm motivated, of course, with the new applications of ChatGPT-3 or ChatGPT-4 now. So we know that the ChatGPT-3 can be used to produce a text that is almost indistinguishable from human being. So for example, just for fun, I just ask, can you write a poem by yourself? Something is spit out. I don't know if it makes sense or not, but oh well, it can create poems. Of course, things like, prove something about math, some simple proofs like we teach in discrete mathematics, that of course, piece of cake. So that can be done as well. And we have a lot of other applications, some of them are good, some of them are bad. So we can, write some kind of a summary that of course could be useful, but it can also be used to write software and malware. So all good and bad things at the same time. And it even started publishing papers. So we'll see, it is predicted that maybe ChatGPT-3 will be, will be the main, the most cited, object in a few years. But so far, we have a few papers already published that were produced by ChatGPT-3. So now we have ChatGPT-4, and it passes a lot of tests. So again, we can say that we are far away from artificial intelligence, but on the other hand, if we can pass the low bar or some standardized test better than what we would do or our students would do, then I think that's already a bit scary. So that's what can be done, and of course you can also produce pictures, and I think that's probably even more and more challenging to distinguish from the text, because text maybe you could think I can distinguish, although I think currently it's like 51%. Like if human experts evaluating the text, they have a 51% chance to detect that it was written by ChatGPT-3 versus human being. So it's almost like tossing a coin. And here probably we're hopeless, right? Like all of those pictures are fake photos, but I don't know, probably would we wouldn't be able to tell. So the story is that that what industry partners and I guess governments, we have 2 representations and so on. So I think everyone recognizes that a network could be useful. And again, this is like preaching to the choir. The standard approach is that we live in a connected world. So if you want to understand, how viruses spread, or you want to understand how information spreads, how misinformation or information, and all kinds of almost all aspects of our lives, we have some kind of network in the background that affects this process. So here the idea is that, and I think we'll have at least one talk in this conference. For example, Ash will talk about is there a way to detect bots, for example, by looking at the structure of the network. So the idea is that if text is indistinguishable, if photos are indistinguishable, then maybe the network around, say, bots and non-bots can be used as a predictor whether we're dealing with bots or not. So again, network could mean graph, hypergraph, and other stuff. So let me not talk about it. And books are written and programs are maybe advertisement. I think yeah, this program is worth advertising. I think that's Remco's program at MSRI. So everyone is excited about networks, and we see it everywhere. That's kind of the bottleneck. So that's kind of like the summary of the motivation. And it's not surprising because, again, we live in an increasingly connected world, and these networks are getting more and more important, and everyone recognizes that. But now let me put the other hat and say, okay, great, networks are fantastic. Is there anything bad about networks? And when we talk to practitioners, sometimes they complain. So what are the common complaints that we hear? I guess one complaint that we hear is that, well, we have this large but sparse, which is good, of course, adjacency matrix, but getting anything out of this matrix is difficult. And not only difficult because even if I want to know who is close to who, that will take some time. I cannot have a constant time algorithm to determine the distance of the shortest path. But if I ask, for example, who is similar to this vertex, first of all, what does it mean? And second of all, how to measure the distance between nodes, that's also difficult. So graph itself, of course, is useful, but we cannot answer many of the important questions just looking at the matrix, or at least we cannot do it quickly. Another example is that, well, we have many friends on the Instagram. You model this as a graph, great. You know your neighbors, maybe you know your second neighborhood, but not all my friends on Instagram are similar to myself or similar to each other. How we could fix this problem? Well, we say, yes, that's easy, weights. Sure. But maybe more important, there could be some other users in the context of bots. There could be a bot in Canada, or it could be a bot in Poland. They're similar to each other, but they're far away from each other. So there's some similar objects, similar nodes in the network, which could be far away from myself in the graph sense, but still similar. So adjacency, again, matrix is not telling us that information.
What is similar?
Yeah, that's what I said. You have to define this first. What does it mean similar? And of course, there are many different ways one can define it. And the easiest for graph theorists would be the distance in the graph, but that's of course not so much. But it can be my neighborhood is similar, or maybe my I don't know what the number of some motifs around myself in my EgoNet is similar, and so on. So you can, of course, and that's the first thing, you have to define what does it mean to be similar, and then try to capture that. And that, of course, application driven, right? So there's no standard way to measure similarity. So here it is. The picture is as follows. So what practitioners say these days is that, well, it's kind of maybe the other way around, because some of us complain, well, I don't want to play with vectors. I like relational data with which I have relations, but now we're kind of going back to vector space, but we want to go back to vector space in a meaningful way. Namely, if I give you a graph, I like it, so don't get me wrong. I'm a big fan of networks, of course, but if I have a graph, I can enrich this data set by trying to extract important information. So what does it mean? I want to come up with, I think I can start using those nice features. So I can try to find a function that assigns to every node in my graph a vector. And the idea would be that this vector kind of encapsulates what I want to measure what I want to use for my machine learning application at the end of the day. So the idea will be that, I want to now look at the graph, of course, but try to extract something important to map every node to the vector.
This is also extended to settings where the vertices are active. That's one of the common complaints.
Yeah, the vertices, I'm sorry?
The vertices are active.
Yes, so, right. Yeah, that's a great question, and I think there should be something on the slides. Yes. I think that's probably what you're talking about here. So I can extract the structure of the network and represent the structure of the network around the vertex as a vector. But then if I have additional information such as, as you say, maybe age, maybe beliefs, maybe some other information about the node, I can basically add this to my vector. But more importantly, these additional features can be actually used together with the embedding algorithm to produce the embedding itself. So actually, this could be done in the same way. And algorithms such as Refix and Rolex and many other things are trying to capture exactly that. So not only how my neighborhood look like, but what kind of neighbors I have. So I'm trying to learn the structure around the node, as well as the behavior, the type of my neighbors at the same time. So yeah, so the goal would be to preserve by this vector the structure as much as possible, and either graph structure or, as Bogomil was saying, maybe I care about some other similarity measure. So if I care about something else, maybe I want to preserve by these vectors the distances between nodes, but not in a graph sense, maybe in some other metric that I care about. Already we talked about this additional features that can be injected, so that's also easy and in some sense for free. And those embedding algorithms are very often, ignoring the noise, meaning that they're forgetting about useless information, but trying to extract the informative information, like the most important information out of the graph, and that could be useful. There are many things that are known. I'm not going to mention most of it, but for example, hyperbolic spaces come naturally into this picture, because as we know, those networks are scale-free, meaning that if I zoom and look at Instagram induced by Canadians, the structure and the behavior of that subnetwork is very similar to the global network. So I would like to have an embedding which kind of has enough space to embed nodes, and for example, hyperbolic spaces are naturally suited for that task. So there are many interesting things happening, and one can extract important information in some non-trivial way. And of course, if that's done, then we can use a lot of tools available. So of course, we heard about clustering algorithms, for example, this week. But if I have vector points in the vector space, then I can go back to classical algorithms like even k-means or HDB scan, and I have many tools available that I could use for vector spaces. So that's also a big advantage. All right, so we're back to the main topic, graph embeddings. Yeah, any questions, any comments? I don't know, I don't want to go too fast, too slow. Yeah.
Just thinking that at least the graph embedding maps each vertex into a vector. It's kind of still mapping that much the whole graph, right? So
yeah, that's an embedding that maps vertices to vectors. You could have embedding of edges. That's kind of course similar, but could be treated in a different way. You could have embeddings of the whole graphs. This is also something of interest. For example, in chemistry, you have little graphs, because it would be silly to try to compare maybe Facebook to Instagram network. But if you have little graphs like representing molecules, you might want to embed the entire graph. So assign one vector to the entire graph, and then you want to have two vectors to be close to each other if graphs are similar to each other. And again, what does it mean similar? Well, you need to specify that first.
I was just thinking that the simple F is there, like I think the embedding is kind of taking the whole graph as input and then outputting that function.
Yes. Yeah. But the function is from the set of nodes to vectors. Yeah, Cliff?
There's also been discussion this week and last about software embeddings. Is that anything you can speak?
Yes, of course, embeddings, as I said earlier, there's a reason for embedding, right? We don't create these functions just for fun, but at the end of the day, we would like to apply them to some downstream, machine learning task. And depending on the application, it could be useful, right? So for example, if I want to capture, if my embedding aims to capture the distances in the network, I have many algorithms that can do that. But if I, for example, for bot detection, that will be useless, right? Because again, I can have a bot in Canada, I have a bot in Poland. They are in a graph distance or far away from each other, but maybe they play similar role. They look the same. And what you talk about is known as a structural graph embedding, which tries to capture the local structure around a node, because that could be an indication of whether I'm dealing with, say, hap or not hap. I'm dealing with bot or not bot. Am I dealing with, a researcher in the collaboration network that brings two communities together, or maybe that's a leader of one community, so things like that. So yeah, so there are many different embeddings. I think we called embeddings that try to capture the distance in the graph sense, like classical embeddings, but there are also structural graph embeddings and embeddings entire graphs and whatnot. So, yeah. But the framework is of course the same. I want to at the end of the day have a function from the set of nodes in this type of embeddings to the vector space. But what that function captures, that's up to us. And traditionally, a lot of work was done around capturing distances in graphs, but now the structural graph embeddings become more and more popular. Definitely more work will be done there. So when we entered this space, there was a main concern from practitioners was as follows. They said, well, look, we have at least 100, now maybe more, we have at least 100 different graph embeddings out there on the market. And many of them are randomized. And even if I like one type, there are 3 different types at least. Some of them are using linear algebra to create the embedding. Some of them are based on random walks, and those are actually quite popular. And some of them are using deep learning networks. So there are even different families of them. And again, even if I like, for some reason, one algorithm, this algorithm is randomized. It has parameters. So I don't know which parameters to pick. If I pick some parameters and embed my graph 7 times, I get 7 different embeddings. So practitioner says, well, I don't know what to do. At the end of the day, I produce like 1,000 different embeddings. Which one should I use? And of course, if my machine learning task at the end of the day is supervised, then I can, of course, evaluate them and pick the one that is the most useful for me. But sometimes it's not possible, and simply that is a long process. So the complaint was that this is the state of the art, and data scientists waste a lot of time trying to pick the right embedding. And again, I'm not touching many of those other aspects. So not only these 3 families, but there are also some dynamic graph embeddings, and we already mentioned about structural graph embeddings, embedding of edges, and so on. So now here, I don't know if you care, but some of you might think, well, wait a minute, like how is that even possible to capture something? So I don't know how many of you know things like word2vec or some other embeddings of words. So the idea is that I want to have an embedding of words. Given that I have a large set of documents, I would like to have embedding of words. Again, I want every word to be assigned a vector, and I want vectors such as queen and king to be embedded close to each other. And for example, flowers and computer, maybe not too close to each other. So I want to have a kind of a way to measure the distance between words. So how it is usually done, or one of the simplest approaches would be to do the following. I go over my document with a window, let's say, of length 20. So I have my word at the beginning, in the middle, and then I know who is on the left, who is on the right, and I can try to estimate, what is the probability that my word is surrounded by some other word. And using this, I can build my vector so that this probability can be approximated by the distance between vectors. And what it has to do with graphs? Well, one of the algorithms, which is actually quite popular, Euler-Escovitz, I guess, was the main contributor, Node2Vec, does the following. Why don't we just run a bunch of random walks? Every random walk is a sentence, and my words are nodes. So I'm again generating random walk. I'm a node. Some random walks go through me.
How the original graph was created?
Well, any graph. So pick Facebook graph or whatever.
So, so what you're saying now is not necessarily related to embedding of words. So it could be embedding.
So the embedding of words, I described what it does, right? And now how one can use the ideas from embedding of words to embed graphs, nodes of graphs.
Okay, so it was just inspiration.
Inspiration, yeah. Well, all I'm saying is that if you know how to embed words, just produce random walks, treat them.
Some sentences, right? So
Yes, and then your random walk is a sentence, and your word is a node. Over.
that was an inspiration for this.
That's that's how to adapt their word2vec to node2vec. Yeah. Yes or no? Maybe. Yeah.
So if you are NLP expert, you don't have to explain us
anything. Yeah. So So I explained, this part, right? So yeah, sentences are random walks and nodes are words. But I said a little bit more for just in case not everyone is aware of word2vec, but I guess that's. Well, so I think again, this picture is stolen from somewhere. So, but it's just two communities, and the idea is that I want my embedding, and as you see at the end of the day, I don't know why I'm not using this fancy stuff. I know that's too fancy for me, but at the end of the day, I have embedding, and you see one community is embedded in one corner of the space, and then some other embedding the other community, red community, is embedded in the different part of the space. So how is that possible? Well, again, the idea is that if I run my random walk, of course, red nodes will have a higher chance to be surrounded by red nodes, and green nodes will have a higher chance to be surrounded by green nodes. So it's like a queen and king. King and queen that are red, let's say, will be close to each other more often, but flowers and computer are from two different communities. They will not be very often close to each other in this random walk. So that's why and how it works. Yeah, any comments, questions? I don't know. So yeah, here's some little pictures, and again, just two examples, but to show you that it actually works, because again, you might think that that's a nice approach, but maybe it does work. But no, it works, and practitioners are super excited about that. So here's just a silly example. I took a karate club. I don't know, am I winning the competition? I think. Yeah, so is that the first talk with karate? No, someone said this earlier. Oh no. All right, so next time we have to put me first. Anyway, so we had the karate clap. We ran deep walk to produce 128-dimensional embedding. A deep walk is one of those random walks. So very similar to Node2Vec, but different. And now, in order to have a picture, we produce a two-dimensional. We reduce the dimension to 2. So usually we use UMAP, but again, I stole it from someone else. So someone else used TNSE. I don't know why, but there should be UMAP instead. You would have even nicer pictures, perhaps. But anyway, so this is a 128-dimensional space, which clearly captures the community structure. And not only that, because now you have members of one community, red or blue, but you can also see kind of even overlapping communities. You can try to see how strong member of one community someone is. So this will be maybe someone like a connector between two communities and so on. So of course I can try to use graph techniques to learn that as well. But if I have a vector, it's much easier for me to determine the functionality and other aspects of that. So here's something more. Sure.
How do you choose the output dimension? Like, for example, in the word embedding, how does the choice of the output dimensions?
I don't know. Yeah, maybe Francois. I hear that you want to say something, but you mean like this the output dimension or after the compression?
Two dimensions.
Yeah. So if you want to know like the state of the art, the best algorithm for dimensional reduction is UMAP, which is developed by Tata Institute. That's state of the art, the best algorithm out there, and it's complicated on one hand, but on the other hand, there's lots of cool math behind it. So maybe let me try to say it. I think we have time, and Francois can correct me if I say something wrong. But the idea is kind of cool. You start with high-dimensional vectors. And the problem with high-dimensional vectors, that's a completely another 3-hour talk. In high dimensions, you cannot trust the distances too much because everything is at the same distance to everything else. So it's a really complicated task. But what you can do is you can build a graph. You can build a so-called k nearest neighbor graph. So every vertex is connected to k nearest neighbors. And then you look at this graph and then you say, okay, now I forget about vectors. Let's try to capture the topology of that graph. So we are using, well, they are using topological graph analysis to understand, who is close to who, and things like density type of algorithms are used to create clusters and so on. So many interesting things is going on, but at the end of the day, you want to create a low dimensional vector, but you want to preserve distances as much as possible. And for that, the minimal transportation problem. So you build things like earth mover distance. You try to solve the optimization problem, where you try to say, I want to have low dimension, but I want to move as little dust as possible to compare these two distributions of distances.
So, but if I can
Sure.
So 2 dimension is many dimension. That's for sure. TSNE is a also very good algorithm in 2 or 3 dimensions. UMAP is also be good in higher dimension. I can reduce your problem to 16 dimension and feed that to the cluster algorithm. But 2 is really for visualization. And the 128, or choosing the dimension of the embedding, that's part of what I'm going to talk about. That's one we have that time.
The k nearest neighbors, the k is not related to that, or is that's an extra parameter?
K is a parameter UMAP.
Yeah, but it's not related to dimension.
No.
Yeah.
May I have a question to Francois?
Sure. But I'm speaking today, so you should
Okay,
be asking
so it's a
questions.
question to you now.
But I'll forward it to Francois.
For you. So why would I create k-nearest neighbor graph instead of using the original graph in UMAP?
You don't have a graph.
You don't have a graph, that's a vector
I
space.
have, because I just embedded it.
You mean like, well, this, in this case? No, I think, so UMAP, but UMAP is just for dimensional reduction for the vector space.
I know, but if I know I'm using UMAP to reduce dimensionality of graph embedding, why wouldn't I use the
That's an
original
interesting
graph?
question, but UMAP is designed for vector space, for point clouds.
No, but has someone considered it like, if I know it's embedding, why would I do k-nearest neighbors? Because my idea was, okay, maybe
But
it's
no,
because
but I can
it's-
answer that, right? So, but which graph? Like the initial karate graph?
Yeah.
Yeah, that's silly because maybe my my embedding is capturing structure of the net nodes, right? So 2 nodes, for example, if I want to know where is HAP, then 0 will be close to 33 in the embedded space, which might not be so close in the graph space. So, or for structural embedding, yeah. But for natural, yeah, for the classical embeddings, yes, you probably could try to play that game, or maybe even try to play the game. You combine the 2, maybe somehow, right? So yes, that's possible, but I think it's like this part should be, it's just agnostic. We already trust the embedding, and we just want to reduce the dimension. I think that's the idea.
Yeah, because why I'm asking, because my thinking was, has anyone checked if maybe this k-nearest neighbor graph is kind of less noisy than the original graph in some sense, so that the embedding removes some noise.
Probably, yeah, should be true.
But I don't know.
Because you can have some kind of sporadic long edges, right? As we all know, right? So, for example, if I look at my Instagram, probably many of my friends are Canadians, but I have some sporadic friends to Poland. So, like you might want to cut them as a noise.
Yeah, that's why I thought maybe it makes actually sense not to use the original graph, but I thought maybe someone checked it.
Yeah. So we can wait in 20 minutes, you will say. You check and you report.
128, is that the length
Of a vector. No, this is just the final the dimension of the vector space.
Okay, but is that related to the random walk length?
No, the random walk length and then how often you restart and things like that. This is just a parameter of the node to vec, or in this case, maybe deep walk also has bunch of parameters. But yeah, that's kind of the dimension. The final dimension has nothing to do with the parameter. So it's always a parameter of the algorithm, but that's not related to the length of the box.
Every node is attached 128 real numbers.
Yes. Yeah. And usually, again, that's kind of the game we play, and then again, the framework will answer that question, but that's another thing that data scientists have to pick, right? So, they pick 128, 256, but why that number? Because it's a 2 to the some power, that's maybe the answer, but nobody knows, right? And very often, actually, we overshoot, and that's another thing, right? So, people say, oh, let's play safe, and they go for high dimension, but of course, that's risky because, first of all, you're not reducing noise. That whole idea is to forget about useless things. So if you go for high dimension, you overtrain your embedding. But if you go too small, you don't capture what's enough. So it's a mystery. Where is this best choice? And our framework will be able to answer that on top of other things. So yeah, let's maybe jump to the embedding, the framework quickly. But here's another work. So if I look at citation, sorry, is that citation? I think that's probably different papers, right, in machine learning community. So if you visualize the network, nothing really is happening. I don't see communities, but for example, if I do the embedding, you get embedding that nicely groups together the same theme of the paper, but just looking at graph structure. And this picture is supposed to convince us, I guess, that for classification, it actually works extremely well. So I can use this embedding, and I should be able to detect which field this paper is from. So here is the framework. And again, I think we motivated the framework, the need for the framework a lot. But let me just say one word, which of course every data scientist keeps in mind, is that if I want to use the embedding for, let's say, detecting bots, or I want to use the embedding for classifying users on Instagram, if I pick a wrong embedding, then we have this garbage in, garbage out mantra that, you know, regardless how good our algorithm is for this particular task, if on the input we inject something useless, something weird, it's not going to be the case that the outcome will do a good job. So here, you know, is the same graph. I don't know if you like my plot. Hopefully you do. I did it by myself this time. So it's the same graph embedded twice. And I don't know, I hope you agree that the embedding on the left preserves more information than the embedding on the right. But how do we do it, and do it in an unsupervised way? So our framework aims to give a score to every embedding and give a good score to embeddings that are nice and bad score to those embeddings that are not so nice. So for a given graph, perhaps I have many different embeddings, and some of them are in dimension 128, some of them are in dimension, I don't know, 64, and our divergence score is going to spit a number, and that number tells me how good the embedding is. And that's, of course, in an unsupervised way.
So those two graphs, why one of them is good, the other is not good?
Yes, well, visually.
So you're assessing embedding.
I'm assessing embedding. So the graph is going to be the same. So graph is one single graph. Pick your favorite graph, I don't know, Instagram graph. And then you give me 100 embeddings, and I run the framework, and the framework spits 100 numbers. And then those numbers will tell me how good the embedding is. The smaller the number, the better the embedding. So I'll just look at those numbers, 100 numbers, and I pick let's say I pick the embedding that has the lowest divergence score, and I say, let's use this one.
So the edges are not part of the embedding, that's just for visualization.
Yes, so edges are part of the graph, and the embedding is just n vectors. But of course, in order to evaluate the embedding, I need to know the graph. So I have one graph and 100 embeddings. That's kind of what you should keep in mind. And perhaps the dimension of each embedding is different.
So is this the low dimensional representation of the same graph with different embeddings, what we have on the slide?
Well, this is just a silly example, but yeah, like, I don't know, I understand the question. So yeah, you have.
What does this do?
Yeah, so it's the same graph, but it's a different embedding, two-dimensional embedding, right? So I embed nodes, and you know, arguably the left one is good, the right one is bad, because, for example, nodes that are close to each other in graph sense are close to each other in the embedded space, but here not so much. So for example, if I want to build my recommender system for new friends on Instagram, you know, if I inject this embedding to my recommender system, then this user will get a recommendation, oh, you should connect to this user because it's very similar to you. Connect to this person. But no, well, this is probably this vertex and this is that vertex. Well, not so much. So if you put garbage in, even your recommender system is fantastic. If you are using embedding that is noisy or is not capturing what's supposed to be capturing, you have a problem.
One of the difficulties here is getting good divergence score. Because when is an embedding good?
Yes.
And you want to quantify that in
Yes.
one number.
Yeah.
That's going to be the challenge, right?
Well, we like challenges. Well, the good thing is that, you know, we have practitioners that actually use these things and need these things, so it's always easy for us to, well, that's why we like working with Francois, not only that he has lots of great ideas, but also, you know, we can test immediately if the ideas work or not. So here's the picture, and I guess, I think I promised Cliff that, I'll reuse the picture. So here it is again. What do? I have a graph. And first of all, what do? I want to kind of look at the graph from large distance. So I don't know, this could be like a, graph limit, a bird's point of view or whatever. So I don't want to pay attention to the whole graph, but first of all, I want to detect communities. So what do? I run a clustering algorithm. It doesn't have to be the best. It's better if it's stable and useful. So you use your favorite clustering algorithm and you get a partition into L communities. So this is what this picture is supposed to represent. So I have embedding. I don't look at, I look at the graph and I assign nodes to different communities. So I have a blue community, red community, green community, and yellow community. And now I uncover edges and I compute how many edges I have in each part and how many edges I have between parts. So it kind of extract kind of bird's point of view, how my how my graph, because I'm not using the embedding at all yet, what is the structure of my graph? So also you can think about, stochastic block model, you name it. So we just look at the distance in the graph and extract densities of communities and densities between communities. So embedding is not used to produce these CIJs, these communities. But now I do the opposite. I forget about graph. I only look at the embedding one at a time. And what do? We generalized Chunglu model to include geometry, meaning I have the random graph model in which the probability that two nodes are adjacent is a function of the distance between those nodes in the embedded space, but also it takes into account the degree of that node. So I don't tell you edges, but I tell you the degree. So you can probably sense that we were inspired by the modularity function here, because that's exactly what it's done in the modularity function. So I look at the embedding, I build a geometric Chunglu model on top of it and compute how many edges I would expect in this null model, in this geometric Chunglu model in each community. And again, note that here I'm not using a graph. Of course, I'm using embedding and also I'm using the degree distribution, but I don't see edges. I just compute how many edges I would see in each of the part in a random graph model underneath. And the idea is that embedding is good if it has a power to predict the densities well enough. So if I give you the embedding, I tell you the degree distribution, and now with only that information, you can uncover, you can predict the densities up to a good degree, then I claim that the embedding is good. And again, that's a question. Do we think it's a good idea or not? But that's what we decided to do. So I don't want to pay attention to links. So for example, another evaluation could be, is this embedding good for link prediction? And we did that as well. But that's a different evaluation, which I'm not going to talk about today. But this kind of is the idea, like, is my embedding preserving communities? So it's kind of from communities' point of view. Question. Yeah, so I skipped that because I don't know, we can talk about it. It seems like I'm not going to talk a lot about algorithmic issues anyway. But yeah, this alpha is interesting. So also in the model, we would like to inject the information what is my aversion to long links? Because I can have a random graph model in which I really don't like long links, and I can have a model in which I'm okay with long links. So this is kind of tunable parameter of the model, which captures, what is my aversion to long links. And we don't know it upfront, and that's actually interesting. We would like to see, we would like to minimize the divergence score over all choices for alpha. So we kind of test the aversion and pick the alpha that fits the bill as best as possible. But something that, for example, I have a few papers with social scientists. So, for example, this kind of aversion for long links is very interesting to them, because we have this homophily and aversion, and we know that it produces polarization, it produces segregation. So this is an important topic, and I think we didn't use it for anything yet, I guess, but one direction is to try to assign alphas to our networks or to our embeddings, and that also is an interesting information, how much I hate to create long links. Because some networks could be more random-like, where random long links could occur, but some of them are really geometric graphs that, like my friends are only local friends. Sorry? Yeah. Power grid, for example, yes. Like we have some limitation, physical limitation, or maybe I don't like using technology, then of course I'll be restricted to friends only, which I can see on the street. So we try to find this, and that's our score. And again, this is an example. I think we took a LFR graph with known communities. I don't know, 100 different embeddings, and I even remember, maybe Francois or Bogomi remembers, but I don't know if even we tested for this particular picture different embedding algorithms, or maybe this is just the same algorithm, the same parameters, but 100 different instances of the same algorithm, because things like that could happen. That I use Node2Vec, I use these parameters, I use this dimension, boom, I have 2 different embeddings, the same parameters. So technically, I should think, oh, they're the same, but some of them is good quality, some of them is bad quality. So on top, I hope you agree, and that's what our framework detected. That's the best embedding, and on the bottom is the worst one. So visually, of course, it's not a proof, but visually, I hope you agree that communities are much nicer separated on top, and at the bottom, they're all messed up, and there are lots of long links. So this embedding definitely didn't do a good job capturing behavior. Yeah, Gane, a question?
Have you tried to add the loss function as your learning embedding? Because if you already know the top one is better, if you add it in the loss function.
Yeah, well, that's definitely a game one can play, but yeah, we wanted to have some embedding, some evaluation that is completely unsupervised by nature, because again, and that's another thing. I said pick the best because for papers and visualizations we only pick the best, but I think if you want to play on the safe side, what you should do as a data scientist, instead of you can generate 100 embeddings and pick 5 of them that score the best, and then you take your favorite magnifying glass, whatever supervised machine learning algorithm you do, and then you pick out of those 5 the best one. Yeah, I don't know who is. Yeah, Rios.
Did you ever observe in practice that one embedding might look good with one divergence metric, but then not good with another?
Look good. Like you mean like if I project to 2-dimensional and just eyeball them?
Well, I mean like the number that you get.
Yeah, I don't know if I understand the question.
Okay. So this is only 1-dimensional score, so it doesn't answer your question, but we do, as Pawel mentioned, we do have this link prediction score, which is much more local. And one thing that can happen is that you have an embedding that will be very good at separating the communities. So this would be good with this measure, but it squishes them all together very, very tightly. So inside the community, you can very poorly predict where there are edges, the prediction process. The second thing that we introduced at Pawel is the second way of doing divergence, which is more local, but it's not going to be covered, obviously. Then it could give you different results. So in the full-fledged version of the framework, you can play with both, and you get kind of a two-dimensional objective. So yes.
So I misunderstood the question. So if you ask about these two different evaluations, then we usually, and that's what we ask our data scientists to pick the best embedding from, is that you plot in a two-dimensional XY plot, you plot all the embeddings so that you can eyeball and see, oh, maybe I want to go for slightly worse embedding in the sense that the community are not preserved as best as possible, but for link prediction, it's equally good, or it's also working well. So depending on the application, you can look at x-axis, y-axis, or both. That question?
No, I just wanted to add that this is exactly why we thought of using this as an objective for doing the embedding, but this measure captures only this global aspect of the quality of the embedding, so that's why we rather think of it as an assessment tool rather than a tool to actually perform the embedding, because it ignores this lens look at the individual node.
Mm-hmm. Yeah, because also we think about this maybe a Bayesian approach that maybe not all of my edges are measured, maybe some of them will be created soon, so I want to kind of have from BERT's point of view, I want to see that yes, my embedding is doing a good job, but I don't want to pay attention to particular edges or non-edges. This is another football graph, another famous little graph toy example, and again, the top one, I guess, is the best embedding, and the bottom, the not so good embeddings. So I don't know, I have 0 minutes, maybe, I don't know. Any comments, questions, or I should keep going till I have 5 minutes? Yeah, we had some questions, so maybe, I can stop if someone has questions. One option would be to just answer questions, but if no questions, I can show you quickly some scalable algorithm. Yes?
So you mentioned good embeddings and not so good embeddings, but can you also name them so that we have some information?
Okay, that's a good question. So the whole reason why we do it, because one approach will be to just do a grand study, like we have 100 graph embeddings. Let's just, I don't want to say hire master student, right, to evaluate, to test all of them, but let's just look at them, evaluate them, and then at the end of the day, we say node to vec is the winner, and then use node to vec. But unfortunately, it's not true. As I said, for different graphs, for different machine learning tasks, and different embeddings perform differently. So there's no clear winner. And also for different graphs, sometimes this dimension is the best, sometimes that dimension is the best. So you cannot upfront decide which algorithm is going to be performing with high probability the best, and what dimension I should be using. That's all black box. So I think that's why there's a need for the framework. So yeah, the different graphs, different sizes, different densities, different structure of the graph, different algorithms are going to perform differently.
Then just a small point, what you already said, but it's very relevant. If you run one algorithm 10 times, you get 10 times completely different things, because most of those algorithms are randomized.
Yeah, so
if you have two different embeddings, is there a way to measure how similar these embeddings are to each other?
I guess we have one way. We can extract these vectors and do it, but yeah, Earth mover distance, but because you have one distribution of points, you can think about it. So we just compare two distributions.
It works with like rotations and
I don't know that well. You can take it into account, but yeah, that's already, as you see, complicated task, right? Yeah. And also, I can have two embeddings that are far away from the earth moving distance, but kind of from the application point of view, they could be equivalent. But maybe what I should say, because it seems like
The simpler thing also, we can look at the previous neighbors. Even
but yeah, maybe one thing I should say, algorithm might be scalable, algorithm could be also interesting, but I guess, I don't know if I have time to maybe just show you one slide or two, but maybe so far it looks like eyeballing, but of course, for presentation, the pictures are always the best, but of course we did test how the divergence score correlates with the quality of the embedding. So, we can use the embedding for clustering, you can use embedding for link prediction, you can use embedding for many different machine learning tasks. And then you can, of course, easily play the game where you say, let's see if there's a correlation between this unsupervised divergence score and the quality of the embedding for a given machine learning task. And that's, of course, the real proof that the framework does a good job, because we have a 128-dimensional embedding. We projected 2, so eyeballing is nice. We like looking at the pictures, but that's definitely not an evaluation that one should be using for seeing if the framework is doing a good job. So of course we did much more serious stuff. So anyway, I'll probably just skip that. I don't know if I have any cool pictures, but the main idea for the algorithm, and maybe I'll just say one word, is that we have to run this framework for many embeddings. But what's scary is that in practice you have graphs with billions of nodes. So we cannot afford anything that is not almost linear. So you cannot, for example, have a quadratic complexity, and in order to compute the weights in a generalized Chunglu model, you have to spend quadratically. The running time is n squared. So one more time, in the geometric Chunglu model, I would like to have, I would like to find. Oops, yeah, I did this at the very end. Yeah. I did it on purpose so that you don't feel bad. No, I wanted to press that button. Yeah, so we want to tune the weights in such a way that the probability to see an edge between vertex I and j to be a function of the distance, but also I want to tune those weights so that at the end of the day, the expected degree is what I want this to be. So in a Chunglu model, of course, there's nothing to do. We know exactly what the weight's supposed to be, but in a geometric version, you have to tune them. And in order to tune them, that takes n squared time. So the whole business behind the scalable algorithm is that I want to group together nodes and replace them with the landmark, and the weight of the landmark can be used as a weight for all the nodes that are part of the landmark. And that's approximation algorithm. And we do it in a fast way, because again, all we can afford is n log n. We cannot just go crazy and do it properly or do it slowly but carefully. You have to do it in a super fast way. So we use some kind of ideas coming from PCA, but at the end of the day, here is again picture that here's the exact divergence score, and here is what was spit by the approximated algorithm. So maybe we're not perfect, but we're almost perfect, right? Maybe we're not perfect, but at least the order that the best ones are not affected. So not only quickly, and I don't know if I have this slide. Not only we can do it quickly, but also, as you see, it works. And how many landmarks, you might ask? Well, that's obvious, root of n, because if I have a quadratic algorithm, I want root of n squared to be n. So that's how it works. thank you so much.